Today we are going to start our last topic of section 3 related to waves. This is related to subtopic as sound waves over there or sound over there, sound waves, in which we will study about the characteristics of the waves, and we will also study about how the waves are produced and how waves travel from one point to another in the form of energy transfer. And when you hear sound, then you can say when vibrations reach your eardrums, then it is going to vibrate and sound can be heard. What you hear depends on the perpendiculars, or we can say, of the sound wave that reaches you, as well as how much you are got down towards that loudness over there and laugh holes over there. So I will talk about here sound travels, how sound travels. Sound travels as waves over there, as waves over there. These are called longitudinal waves. Longitudinal or compressional waves. Waves over there. In longitudinal or compressional waves, I will say they move parallel to the particles of the medium. Parallel to the particles of medium. Moves parallel to the particles of medium. For the production of sound, I will require vibration of the medium, vibration of the particle which is producing, vibration of object which is producing sound is a compulsory basic unit, is going to produce the sound. Sound waves are longitudinal waves caused by vibrating objects, and the vibrations are passed through the surroundings medium as a series of compressions over there. Series of compressions are responsible for series of compressions are responsible for the production of sound over there, which are flowing in the surrounding medium over there. Thus, if I show here, if this is the compression, then there is little bit refraction, then compression, then little bit rarefaction, compression, rarefaction, compression, rarefaction are going on. Compression, rarefaction, compression, rarefaction, compression, rarefaction are going on. Due to the alternate of this phenomenon, we can say the sound eventually reach someone's eardrum over there, at which point the person might hear it. The human ear is capable of hearing sounds with the frequencies of ranging audible frequency range of 20 to 20,000 hertz over there. That will be the frequency range which a human ear can listen over there. And actually, when we are getting older, there are some people who are not able to listen more than 15,000 hertz over there. And because sound waves are caused by vibrating particles in general, the denser the medium, the faster the sound waves travels through it. Like I can say I am taking a solid medium, I am taking a liquid medium over here, and I am taking a gas medium over here. The speed will be lowest of sound, and then greater, greater, and greatest in the solid medium over there. When the medium is solid, the particles of vibration is much in the form of vibratory motion. They are closer to each other. Then the speed of sound will be taken much, much faster. If I want to talk according to gas or air over there, the speed is approximately being taken as 340 meter per second to be available for the sound waves to travel over there. And this also meant it can't travel through a vacuum, whereas there are not any particles over there. So these are called mechanical waves, which require a proper medium for their propagation. Mechanical waves over there, they can't pass through medium of space over there. Can't pass space because they require a proper medium and named as mechanical waves, which require medium for their propagation over there. So sound waves generally travel faster in solids than liquids and faster in liquids than in gases. And sound waves will be reflected by hard, flat surfaces and things like carpets and curtains in our rooms over there, and absorption surface over there. And if I say if a room is empty, a room is empty, and there are regular surfaces that are walls over there, then when the sound is produced, it is a reflection of sound, reflection of sound is very arranged manner over there, reflection of sound, which can be named as echo. But when I have some furniture or I have some, I can say, filled up with the table, chair, curtains, the surfaces are not smooth over there, then I will not be able to listen the echo over there. Then that case, I will say the absorption of sound, absorption of sound due to irregular surfaces, due to irregular surfaces of room filled with furniture or like that is called reverberation. Ration over there. I also want to tell you that the distance between two consecutive compression is called wavelength. Distance between two consecutive rarefaction is also called as wavelength over there. And that is just like an information which we have already done with the transverse waves and longitudinal waves in the previous lecture. That was lecture 1 of this section 3 of waves over there. So this was reverberation and echo should be taken into account. And sound waves also refract, change the direction as they enter into different medium. As they enter a denser material, they speed up. And when they speed up, we can say that they are going to be decrease their frequency, increase their frequency, and speed is increasing over there. So in that case, we can say the changes in refraction is hard to spot over there under narrow circumstances or normal circumstances over there. But I will say here, they also show some refraction is also being shown, but not observable in normal situations over there. Not observed or easily observed in normal situations over there. Situations over there. So I think so. Introduction is almost done. Now, how can I display a sound wave on an oscilloscope? That is a versatile graph plotting device over there. A sound wave receiver, such as we can say microphone, can pick up the sound waves traveling through the air over there. Means I'm saying here, first of all, microphone is going to get microphone. If you are speaking over the microphone, it is getting the sound to be recorded as in the form of a signal of sound waves over there. Then to display these sound waves over there, then these sound wave signals to be displayed um, uh, on the oscilloscope, measure their properties. You can plug the microphone into an oscilloscope, and my microphone converts sound waves into electrical signal, like sound waves which are producing over there are to be converted into electrical or digital signals over there. Then oscilloscope is a device which can display the microphone signal as a trace on the screen over there. Means this signal is giving to oscilloscope, which is going to trace the signal on the screen over there. So in that case, I will say here that the appearance of the wave on the screen tells you whether the sound is loud or quiet sound. That trace will give me the information that it is a loud or quiet sound. Quiet sound over there. And high and lower pitched, what is the frequency relating phenomenon according to high and low pitch over there. You can even take a detailed measurement to calculate the frequency of the sound wave by adjusting the settings on the display over there. So pitch is being taken. We can calculate the frequency of the sound wave from the detailed information which is displayed on the oscilloscope from the microphone signal of the sound over there. So I will say loudness increases with the amplitude. How loud is the sound? Loudness of sound is directly related to amplitude of the sound. And pitch of the sound is dependent upon frequency of the sound over there. Frequency of sound wave should be taken into account over there. So the greater the amplitude, the greater will be the, if the amplitude is greater, sound will be more louder in that case. The more energy it will carry, and in sound, this means that it will be louder. Louder sound waves will also have a trace with larger amplitude on the oscilloscope. If I want to show your signal on the oscilloscope, for example, it is being drawn in this form over there. And if you are getting the larger amplitude with the louder sound, then I am saying with the same frequency and wavelength over there, it will have the larger amplitude. Then these are the louder sounds to be shown on the trace table over trace on the oscilloscope screen over there. The higher the frequency, the higher will be the pH over there. Pitch and frequency are also being taken over there. But in this case, for example, I am saying to you that you are given with the higher pitch over there in the form of frequency should be taken. Then we can say, for example, I am getting here the original wave like in the same format, but I say it is given to the higher pitched value over there, then what will happen? That its frequency is increased with the same amplitude over there. Frequency is increased with the same amplitude over there. But if I go with the lower pitched value, if pitch is lowered from the original signal over there, then I will say it is going in the form of like in the form of only low pitch frequency over there. And if it is higher pitched and louder both, then I will make my this signal with the larger amplitude but the same frequency. It is higher pitch, higher amplitude should be taken into account. So remember all of these three cases. When you are with the low, this is your original sound signal over there. Then this is, you can say, uh, high frequency. Then you are saying your this signal is, this is high pitch frequency, high frequency, high pitch. And this one is your lower pitched This is higher pitch, higher pitch, and higher amplitude, higher loudness. So overall, the sound waves are being taken into account how they are going to behave their phenomenon in the case of loudness over there. Remember that frequency, if we define for frequency over there, that is the number of complete vibrations each second, which is passing over there. So if in 1 second, how much the frequency is basically number of waves, number of vibrations passing through a point in 1 second measures in hertz or s minus 1 as a per second over there. So you can compare the frequency of a wave on oscilloscope as I have done in the above examples. On oscilloscope, the more complete cycles displayed on the screen, the higher the frequency. And if the source of sound vibrates at higher frequency and higher pitched, then squeaking its overall effect. If the source of sound vibrates with lower frequency, then also being shown in the above graphs over there. So traces on the are very make you understand the basic phenomenon behind the frequency and the pitch of the sound over there. After that, I will say here that the sound waves are overall being taken into account by setting the wave on an oscilloscope frequency and should be taken into account. If I go towards its detail that we should keep in our mind, that is speed of sound in air, speed of sound in air is 340 meter per second. One more thing which we will mostly use in the form of depth of liquid to find when, for example, submarine is above this surface over there, and this is water surface, and you want to measure the depth of the water should the submarine go under there or not. Then for that purpose, we will say for calculating the distance over there, we will have to take speed multiply time divided by 2. Why I am dividing by 2 here? Because your speed of sound is going down first and after striking, it is coming back. So in the form of echo, it is traveling the distance for 2 times. Then you are using this formula over there. For relating the speed and frequency and wavelength of the sound, you are using the relation V is equal to F lambda over there. And we can also use the relation of frequency with the time period 1 over t as the formula of this sound wave section over there. Remaining all the ways, for example, how you can calculate the speed of sound in the air over there. The main method is, for example, there is a cliff. This is a big cliff. You are standing here and you are clapping your hands and you have a stopwatch in your hand which can measure a time period for you, and you are clapping your hand, the sound is coming from this direction to this direction and then reflecting back also towards you. So you will calculate that stopwatch for the between the difference between the production of sound and to the echo heard by this observer or by you. Then definitely should be taken into account that this person is listening. Then you can use the formula for calculating the speed. Then you will have to speed of sound should be calculated 2 multiply distance over time. So this will be the relation which we will be helping for calculating the speed of sound in the air. It also depends upon temperature. If temperature is high, speed of sound is high. It also depends upon humidity. If it is present over there, then the speed is high. So different scenarios can be implemented for taking the sound waves into account. And this was your a little bit small topic which was related to the wave section over there. Kindly subscribe my channel and Stay connected for the next videos also. Syllabus will be completed in the next videos soon over there. Thank you so much for today. Allah Hafiz.